Swayam Prabha. Digital India. Educated India.
So far we have discussed the free vibration problems of single degree freedom systems with viscous damping. One reason why we did it first is that with viscous damping the fundamental equation or the governing equation of motion remains linear in character. So it is amenable to solution. Second point, that it represents also a very large number of real life situations where we have viscous damping. Nevertheless, it is very important to consider at least a few other forms of damping mechanisms, particularly the energy dissipation due to the rubbing of solid surfaces, which is here present almost in all cases. Of course, with this type of damping, which we call Coulomb damping, as I have mentioned earlier, and the other type of damping like internal friction in the materials and so on, we will consider. But first, we will take up the free vibration problem of single degree freedom systems with Coulomb damping. Of course, the resulting equations will be linear, but fortunately for this system, it is possible to get some solutions without much difficulty. Other types of damping we will not take up, and when a situation arises, we will make some comments on that so far as the results are concerned. But free vibration problem with Coulomb damping we will take up in today's presentation. So the lump parameter model the lump parameter model of a single degree freedom system with Coulomb damping can be sketched like this. The spring, that is the restoring element, has a stiffness K, block has mass M, and the solid friction is represented by that device here, where this force F is the force required to cause a sliding. So whenever the force applied to this device so if I think a movement, if you want to call, so what we will find that if gradually we increase F, nothing will happen until and unless we reach a force F. Similarly, in the other direction also, when you try to press them, the force must exceed in magnitude F so that a relative sliding takes place. So therefore, and when this force is below F, then friction automatically adjusts itself and no movement takes place. Now, what will happen if we want to solve this problem? What we will have to consider first is the equilibrium position. Now, the situation is not like that, that if we leave it at any position, it will come to a position where this spring will have its natural length. No. So, we define, because there will be always a small region in which the spring force, whether it is tensile or compressive, is less than the friction force, then wherever we keep it, it will stick there. So, therefore, we have to now be very particular about the point that the equilibrium position we are considering when the spring takes its natural length. Now, for the two cases, when the mass is moving from this side to this side, that means x dot is negative, friction force is acting in this direction on this. So, when it is moving in this direction, that is the case x dot is less than 0, then the spring force, irrespective of its position, suppose its position from equilibrium position is x. So, the spring force will be in this direction, which is proportional to the stretching or deformation of the spring. Now, the force on this, when it is moving in this direction, will be in this direction, and its magnitude will be constant, because we all know that once sliding starts, the friction force between the sliding surfaces remains constant. So, in this situation, when x dot is less than 0, what will be the equation of motion? M x2 dot is equal to F minus Kx, or Mx2 dot plus Kx minus F equal to 0 for the first half cycle. So, how we are doing? We are stretching this to some position and leave it and allow it to oscillate. So, during the first half cycle, that means from this extreme position to the other extreme position, x dot is negative, and this is the equation of motion. Now, in the next half cycle, when the mass moves from left to right, x dot is positive, then again at the similar location where it was at a position x from the equilibrium position, the spring force will be again Kx, and since it is now moving in this direction, the friction force on it will be the opposite direction. Friction always opposite the relative velocity. So, the equation of motion for this situation, when next half cycle, when x dot is greater than 0, will be or so, we have two equations. The whole cycle does not operate with the same equation of motion, but each half cycle the equations of motions are different. So, to solve the problem, we have to solve it for each half cycle. So, what we will do, we will take up the problem when the mass is taken to one initial position capital X1 and then left, and what happens. So, initial condition to start the motion is at t is equal to 0, x is equal to x1 and x dot. So, it is one extreme position here. So, if we now leave it, what will be the solution for the first half cycle? What is the equation of motion? This is the equation of motion, because once you bring it to this rightmost position and leave it, the mass will go because of the spring force towards left. That means x dot is negative, and this is the equation of motion which will be valid. So, mx2 dot plus kx minus f equal to 0 can be written as or put so then of course y2 dot will be equal to x2 dot, because f by k is constant. Thus the equation of motion in terms of the new variable y becomes. So we find that in terms of this new variable y, it is a familiar equation which we normally get. So therefore, what will be the solution of y? We know that general solution for y will be a sine omega n t plus b cosine omega n t, where omega n is again the natural frequency of the system without any damping. Now, to find out A and B, we have to put the initial condition, first half cycle. So, first half cycle initial condition at t is equal to 0, x is equal to 1, x dot. So, we are putting this at t is equal to 0 in terms of the new variable y. What will be y? Y will be capital X1 minus f by k. This is the relationship. And what will be y dot? Is x dot equal to 0. So, if we differentiate this, we get y dot equal to omega n So, put the initial condition at t is equal to 0, y is equal to this much. And at t is equal to 0, y dot is 0. Putting it here, we get y dot is equal to 0. So, the general solution we get A is equal to 0, this goes, so B is equal to now, when it will stop, that is when y dot becomes 0 again. So when y dot becomes 0, when t is equal to 0, which is the initial point, or when sin omega nt is 0 next time, when sin omega nt becomes 0 again, when omega nt is equal to pi. That is the end of the first half cycle. So what is the, if omega nt is equal to pi, what will be correspondingly value of y? If we put omega nt is equal to pi, cosine pi is equal to -1. So therefore y becomes this much. So y is equal to x minus f by k. So from this we get x at the end of first half cycle is equal to how much? Minus x1 minus that is, if we plot we start from here, which is x1, we come here, again it stops here at pi by omega n. So first half cycle is over. All along x was decreasing, that is why x dot is negative. But the peak amplitude what we had at the beginning, which was x1, now this is less than that. How much is this? It is x1 minus 2f by k, but the whole thing is negative. Next, let us take up the second half cycle. That means what happens when the motion starts from here. Again velocity is 0, x is equal to this much. What will be the next half cycle? Second half cycle. In second half cycle, what will be the initial conditions? Let us have another time at t prime equal to 0, x equal to minus x1 minus 2f by k and x dot equal to 0. So we are measuring now with a different time coordinate t2 prime, and this is the x-axis, and this is the new origin of the time scale. We are starting afresh. We start our clock at this time. What is the equation of motion? mx2 dot. Now when x dot is greater than 1, because now x is increasing and velocity is positive. So, this will be the equation of motion. We can rewrite it like this. And using or put a new variable z equal to x plus f by k. So, x2 dot will be equal to z2 dot plus kz equal to 0. So, we get again same equation with a different variable z now. Now, solution of this will be again z equal to c sine omega n t plus d cosine omega n. C and D will be found out from the initial conditions. What will be the initial conditions? At t prime equal to 0, x is equal to minus so z equal to it is x plus f by k. If we do it, it will be minus x1 plus 3f by k, that is minus x1 minus 3f, and z dot is 0. So, we will again get, by such the way we did it for this, we will find that when we put z equal to 0 z dot equal to 0 at t prime equal to 0 here, we should put as t prime, because it is our new coordinate, new time coordinate. So, from that we can easily find that our c term will be 0, as we had a 0 here. Therefore, and your minus x1 minus 3f by k is the value of z at t prime equal to 0. So, this will be equal to so z is equal to minus now after one half cycle, that is when the second half cycle is completed, that means when z dot will become 0, z dot will become 0 when sine omega n t prime will be 0, that means omega n t prime will be equal to pi. So, z at the end of second half cycle will be that if we substitute this here, we get minus 1. So, minus 1 minus plus and obviously z is equal to x plus f. So, x at the end of second half cycle is equal to how much? x1 minus 4f by. So, when you plot it, So again the peak value of this displacement reduces by 2f by k. So it from minus, that is the peak value was x1 minus 2f by k, becomes x1 minus 4f by k. So after every cycle we find that the amplitude decreases by 4f by k. So similarly in the next half cycle also it will decrease by another 4f by k. That means each cycle the amplitude is decreasing by a fixed amount, which is 4f by k. And the displacement diagram of this Coulomb damped system will look like this. So the peak amplitude, if we join, we get a straight line. The question is now that how far it will continue doing this. Let us consider that it oscillates like this. And let so let us draw a band of width 2f by k. Upper side it is f by k, lower side it is minus f by k on the p-axis. And we know that when from here to here it reduced from capital X1 to capital X1 minus double of this, that is 4f by k. Now it continues. It continues like this. And so what happens, I will show it in a magnified way, that as soon as the mass or the block stops, somewhere in this region, say came like this, and say it stopped here. Now what happens? The velocity of the mass is 0. That means it stopped. Now for this to move, there must be some resultant force acting on it. But what is happening? The mass has come here on the other side of the equilibrium position, and spring is supplying how much force? It will be, if this deflection is say delta, it will be k delta, and it is compressive because delta is in the negative direction. Whereas the friction force if it now tries to move in this direction, friction force will act in this direction, which we call Ff. How much will be the friction force? We know that the characteristics of solid friction is like this, that it always adjusts the friction force to the applied force up to a limit So, the friction force, if it is being pushed in this direction by a force F, then it is subjected to a friction force which is Ff. Now, we all know from our basic mechanics that if we plot Ff versus this, whatever there will be a 45-degree line, that means at every instant F is equal to Ff up to a limit which we call the limiting sliding force, beyond which friction cannot apply any further force. So therefore, if the value of K delta is less than Ff, which is apparent from here, K delta, because this much is how much? F by K. So, Ff, that means friction force, will be equal to K delta, because it is K delta is less than F. Thus, maybe somewhere we are operating somewhere here. So, whatever force is being applied, which is K delta, friction force will immediately balance it, which means that this system will not move. So, therefore, whenever the system stops, it cannot move beyond that point if that stopping point happens within this band. And that is what I mentioned once, if you remember, that real systems always comes to a total stop, velocity becomes 0, primarily because in all real life systems there is certain amount of Coulomb damping present. If it is viscous damping, theoretically it should go ad infinitum to oscillating with smaller and smaller and smaller amplitude. Now, this decrease in amplitude per cycle which we have found out could be found out in another method, which is of course much simpler, as we will see now. We solve the problem by very direct approach, solving the Newtonian mechanics of the problem. So, let us solve the same problem from energy approach. Our system So, again we take up the same problem, that we pull this mass to a position here. And the displacement from the equilibrium position is capital X1 and leave it. Then what happens? So this is the starting position. So if we put the location of the mass, first it is here, capital X1, then in the first half cycle it comes here, and here it is the equilibrium position. So this is the first half cycle, it comes from here to here. In the second half cycle, it goes from here to here. And let this value be x3. So like that, in one cycle, it comes from here to here and then to here. So let us find out the drop in magnitude per cycle. This is the so what is the total energy when we pulled it and we left it? So since the velocity here was 0, the whole mechanical energy was in the potential form, that is the strain energy of the spring, because gravitational potential energy is not playing any role as the whole thing is in the horizontal direction. So energy at position 1 was simply half K, because x1 is the amount of stretch in the spring. When it came here, the spring becomes of natural length. Then it started being compressed, and when the block reached the other extreme position, then the spring was under a compression of x2. So E2 and then again when it went and stopped here, the energy at location 3 finally half. So we can see the energy is decreasing. Why? The reason is simply because when the mass is coming from here to here, it is also dissipating some energy because of this friction. What is the amount of energy lost due to friction when it travels from here to here? Simply, since the friction force is constant, because for any two sliding bodies, the friction force is constant. So the work done due to the friction or the loss in friction will be simply the amount of distance traveled multiplied by the friction force, which is constant. So energy lost due to friction in the first half cycle is nothing but the difference between E1 and E2. And how much is this energy lost is nothing but the work done by the friction force, which is constant F, multiplied by the total distance traveled by the block, which is again nothing but x1 plus x2. And we know therefore that half K into x1 square, if we substitute E1 and E2 here, we get this. Or so straightforward we get the decrease in amplitude or the extreme values of the displacement in the first half cycle is straightforward 2f by k. Similarly, if we do this, so the next half cycle, the energy decreases from E2 to E3. So E2 minus E3 is the amount of work lost by friction, which is the friction force into this distance traveled. Substituting or finally x2 minus x3 so adding these two, thus we get the same relationship or same thing, that the amplitude decreases by an amount 4f by k in every cycle, and it decreases by 2f by k in every half cycle. So we can get the whole thing in so simple manner, but one thing we must remember, it has only given information about x1, x2 and x3. What happens in between we have no idea. So therefore, to get a complete idea about what is happening, complete displacement diagram, we have to solve the differential equation. Energy approach can only give some information about the extreme value. So we should not have the misconception that we can avoid Newton's or Newtonian mechanics and use only energy approach to get the complete solution. It will not give the complete solution or full information, only the decrease in amplitude we can get, whereas the solution what we had by solving the differential equation, it was the complete displacement diagram we could draw. Now I think this complete displacement diagram or complete information about motion we can obtain also by another method, which a technique which we will use that has been explained earlier, that is the phase plane approach. So we will solve the same problem. Now we will get a complete solution, not just the extreme values of the amplitude. We will solve the whole problem using this phase plane technique discussed earlier. First, let us find out the system in masses movement. We have seen that when in the first half cycle x dot is less than 0 and the equation of motion was m y2 dot plus ky equal to 0, where y was equal to So if we plot x by the blue and this is the origin for x and this side is x dot will be same as y dot. Same axis. Then we know that here the solution is something of the order of, we know that y square plus y dot by omega n square will be a circle. That we have seen that this equation solution always leads to a circle in the phase plane where the axes are, one is the displacement, other is the velocity divided by omega n. That we should remember. So only thing what we can do now is, for the, since y is x minus f by k, we have to shift the origin here. So what we will do, originally I showed it here, but it should be shown here, whereas this is the origin now, new origin. So now we have a new axis where this is the y axis with this as the origin, this is minus y. So therefore, wherever we start, say if we start at the extreme position here, x is equal to x1, so y is equal to x1 minus, or say minus f by. This is the starting value of y. If that be so, then in the first half cycle, it will describe a semicircle coming here with O prime as the center and this as the starting point. So here this is y2. Now since it is a semicircle, we should know the magnitude of this and magnitude of this will be same. Now if we go to the second half cycle, x dot is more than 0, equation is m z2 dot plus kz equal to 0, where z is equal to x plus f by k. So therefore now the new axis, new origin will be here. This will be the z axis and this will be z dot by omega n. So now we know that this is the, and we know that z square plus z dot by omega n square will be another circle. Sorry, we should say square here. Not essential, but I think that should be applied. So now in this next half cycle, this will be the center and this will be the path space curve. A semicircle again with this as the center and this point, so you can draw it. So it will go there, and as now we find that the mass has stopped with velocity 0. All the velocities are 0 here, and it is within this band of f by t. So therefore, motion will stop here. And to plot what will be the x versus t, we can easily extend this. We can see that means at any position, if t is 0 here, then what will be the value of t here? That we can find out by taking any point. Say first point is this, second point is this. This angle is say theta 1. So T1 will, T2 will be theta 2 by omega n. So when we plot an xt diagram, or rather I should use this side. Now we get a displacement diagram where one axis is x, other axis is t. So originally we started from here at t is equal to 0. Then at t is equal to t2, this will be the value, and t2 is equal to this. The point will be here. Similarly, we can go to this T3, and T3 will be how much? Theta 3 by omega, and that is the amount of time for the phase point to come from here to here. So T3 will be something like say here, and the value will be somewhere here. So we find that it will come like this. Then next, let us see, let us go directly to this, that is theta 4, and this is the fourth point, and T4 will be equal to theta 4 by omega n, and that will be something here. And here we have gone to the other extreme end. So first half cycle we have plotted will be like this. Second half cycle when we plot, then time you have to calculate from here. So this is T5, or say fifth point. So this is theta 5 now, and T5 will be theta 5 by omega n, and that is, this measurement of time is from now here. So this is T5. This is actually T5, not this one. And for that, of course, we can use different colors. Here. So it will continue. So we can get a complete displacement diagram graphically from the phase plane diagram, and this time, determination of time, how to do it corresponding to various points on the phase plane diagram can be also done this way. So thus, in many situations, the phase plane approach can give us a solution, and without solving the differential equation, we can get the displacement diagram. I think we come to the end of our major discussion on free vibration of single degree freedom system. And as you have noticed, there are two things which we have done. In case of undamped system, our primary objective was to find out the natural frequency of the system. That was the objective of solving the problem. In case of damped systems, it is not only the finding out the frequency of oscillation, but it is also finding out the way the amplitude decreases, or the displacement diagram we want to solve. We have seen in viscously damped system, the time period is slightly increased because the damped natural frequency is slightly less than the natural frequency of the same system without the damper. And in case of Coulomb damping, we have seen that the natural frequency or the time period, it remains same whether this as the undamped system. We have further seen that in viscously damped system, the amount of damping determines the nature of response to its initial disturbance. We have seen if there exists for each particular type of system a value in the damping coefficient which is critical. If the damping coefficient of the system is above that, then the response is aperiodic, but if it is less than the critical value, then the system is periodic, though decreasing amplitude with time. In the next lecture, we will start the determination of the response of a system to outside oscillating disturbance or force. That means we will start our discussion on force behavior.